Hello. Hello again. This is my third video today. I'm still wearing the same shirt. So if you look at the other two, you'll notice that. Otherwise, so it's still the end of July for me. This will probably be my last one I'm making today. So when I come back tomorrow, I'll make another 3 and I'll be wearing different clothes. Anyway, we're going to talk about geographical influences of climate. We're going to describe how mountains and oceans, including latitude, can change the climate of a location. And again, at this point we are in class. You've probably gotten your assigned green home location. So you're trying to figure out how is that particular location, how do the mountains nearby, how do the oceans nearby, how's its latitude, all of those things come together to make the climate of your location what it is. So here we're going to mention how mountains and oceans, if there are mountain ranges nearby, also altitude and a couple other things. So to start off with, we talked about how the farther you are north, in general, the colder it is. The farther you are south, it's warmer. We are right about here. There's Washington, D.C., so we're right about here in Washington, D.C. I lived in this area from when I was a kid, and then I moved to Milwaukee for a little while. And it's not that much farther north, and yet we had much more extreme winters than we did here in Maryland. And also, we had less extreme summers. Sorry, more extreme summers. Right now I want to talk about two places, St. Louis and San Francisco, California. Now those are really close to being the same latitude. And I happen to have some graphs here that show that St. Louis starts out 0 degrees Celsius winters, gets up to about 30 degrees Celsius winters. Like I said, it's in the 90s Fahrenheit. And then it comes back down here. On the other hand, San Francisco stays right around 10 to 15, maybe 17 degrees Celsius, which is right around the 70s. Winter it might get in the 60s, might get in the high 70s in the summer, but pretty much the same temperature all year round. If they're at the same latitude, why is that happening? Now, one thing I want to point out is that if you averaged out the highs and lows, if you took the average, they both have about the same average temperature all year long. But if you go back and you take a look at this map again, what is the difference? If they're at the same latitude, why does one place have more extreme seasonal weather than the other? And when I take a look at this, I notice that St. Louis, Missouri is right in the middle of the United States, while San Francisco, California has some ocean front. And being by the ocean has an impact on its climate. It has to do with the ocean currents. It turns out that the ocean currents, as they come by, they actually bring the temperature of the water as it moves past San Francisco can help moderate the temperature. Another place that we could take a look at, hopefully you recognize this as being, India. So we have India here. And when you take a look at India, India has the Indian Ocean right here. And these arrows represent wind. During the summer for India, the wind tends to blow in this direction. And during the winter, the wind blows in the opposite direction. So let's go ahead and take this video and see what that tells us.
While you know the nations we are currently studying are located in Asia, you may not understand why we call this region Monsoon Asia. Contrary to how it's sometimes used in everyday speech, as in, it's a monsoon out there, monsoon actually refers more to wind than rain. Monsoons are the prevailing sea-to-land and land-to-sea winds that determine wet and dry seasons. The continent of Asia, especially near India, experiences seasonal changes in wind direction, producing either rainfall or drought. Notice on this map, India is located between the huge landmass of Asia and the vast waters of the Indian Ocean. We know that land and water change temperature at different rates, causing instability in atmospheric pressure. This difference in pressure creates wind, which determines the wet and dry seasons. In the summer, the landmass of Asia warms rapidly, but the Indian Ocean is still relatively cool. As a result, that warmer air begins to rise. This is associated with the low pressure system over the Asian continent. Conversely, the cooler air over the ocean begins to fall, creating conditions associated with high pressure. Remember that wind always blows from high pressure to low pressure. As a result, during the summer, the winds blow from sea to land. The moist air blowing from the sea, in combination with rising air over Asia, creates intense rainfall during the wet monsoon season, typically experienced in India from June to September. However, this process reverses during the winter. As colder air settles over Asia, high pressure is established over the continent, but the relatively warmer ocean water creates rising air and thus low pressure dominates. These conditions create a land-to-sea wind pattern, therefore a lack of moisture over Asia. As a result, during the dry monsoon, from December to May, India receives little, if any, precipitation. Take note of how high and low pressure systems impact the monsoon seasons of this region. These extreme conditions have plagued Indian agriculture for centuries, as farmers rely on the wet monsoon season to provide water for their crops. Recently, the monsoon seasons have become less reliable and more dramatic, causing prolonged drought and devastating flooding.
So this idea that as wind blows from water to land, it can bring that moisture onto land, causing it to rain a lot, the wet season. But when wind is blowing the opposite direction, there's no moisture for it to pick up, no water for it to pick up. So it doesn't rain over land. It brings all that dry air over the ocean, and it doesn't bring any water over here. And so we've been talking today a lot about climate and temperature. It's good to remember that when we talk about climate, not only are we talking about the average temperature, but we're also talking about the average amount of rain that it gets, or precipitation. All right, so here's some important latitude lines that we need to remember. North Pole, again, is 90 degrees north. The Arctic Circle is 66.5 degrees north. The Tropic of Cancer, that point when that's where the sun is most direct during our summer, 23.5 degrees north. The equator is 0, and the Tropic of Capricorn is 23.5 degrees south. Antarctic Circle is 66.5, and the South Pole is 90 degrees south. And again, we just remember, all of these different ways that energy can be transferred through radiation, convection, and conduction affect the way that the Earth is warmed up, and that the different amounts of energy being reflected and absorbed affect our climate. That now, we're talking about winds affecting precipitation. So one of the things that affects the winds is something called the Coriolis effect. And the Coriolis effect is related to the Earth spinning. We talked about how wind tends to blow from colder regions to warmer regions. The North Pole tends to be colder. The equator tends to be warmer. So we would expect, in this model, we would expect wind to always be blowing from the north towards the equator. And then, of course, the opposite in the southern hemisphere would be from the south towards the equator. And we'd expect all wind to be blowing towards the equator. Now, like we said, models are not, in real life, are usually a little bit more complicated. So when we add the spinning of the Earth, that ends up making it seem like the wind is blowing east to west as well. Let's check this video out. All right, so here, here we have the Earth, and when the Earth is one thing that's happening is that we have, at the equator, we have air rising, and so along the Earth's surface, wind is blowing, like we said, towards the equator. And then the jet streams, the air high above the atmosphere is going the opposite direction. We have a nice convection current forming. This is happening right at the equator. Now, because air is rising at the equator, it's sinking right about 45 degrees north. At this point, we have a cell doing the opposite. And then at the equator, like we said, we have wind blowing away from, did I say the equator? I meant the south and north pole, we have wind blowing away from the poles. And so we end up with all of these wind systems going on, having to do with the temperature differences on the Earth. Then, when you add the spinning of the Earth, we end up with wind blowing not directly towards the equator, but sort of at an angle. And not directly away from the poles, but sort of at an angle. And that helps us explain some of our winds. Here we take a look at, the video mentioned earlier, high and low pressure zones, where wind blows away from high pressure and towards low pressure. And I mentioned how the wind blows towards the equator, but at an angle because of the Coriolis effect, because the Earth is spinning. And it blows away from the South Pole and away from the North Pole, but again at an angle because the Earth is spinning. And then we call that the Coriolis effect. A prevailing wind is a wind that blows predominantly in a single direction. So when we talk about global winds, we're talking about those big global winds that are always blowing in the same direction. We do have local winds that are affected by local temperature differences that again, make things a little bit more complicated. All right, so let's just take a look at some of the other factors that affect climate.
In fact, altitude is one of 5 major factors that affect climate. If you walked up a mountain pathway, for example, you would find that the temperature would drop 3.5 degrees Fahrenheit for every 1,000 feet you climbed, or 6.5 degrees Celsius for every 1,000 meters. Another of the 5 factors that affect climate is latitude. Because the sun's radiant energy shines directly on areas nearest the equator, that is where the warmest areas of the Earth are found. Farther to the north and farther south, the angle of sunlight becomes smaller, so there's less heat from the sun at those locations. At the North Pole and South Pole, the angle of sunlight is so small that very little heat finds its way to the Earth's surface in those places. Latitude takes on added importance as the Earth makes its annual journey around the sun. That's because the Earth tilts roughly 23.5 degrees on its axis. So when it's at this position in July, it's summer in the northern hemisphere because the sun's light and heat is aimed more directly there. At the same time, it's winter in the southern hemisphere. Half a year later, in January, when the Earth's position is here, it's just the opposite. Now the sun's light and heat are aimed more directly at the southern hemisphere. So it's summer there, and winter in the northern hemisphere. Now, on to the third of the 5 factors that affect climate, the Earth's topography, that is, its surface features. Mountain ranges are an example of a topographical feature that can play a major role in a climate's precipitation levels. As humid air moves in from an ocean and then sweeps upward across the mountain slopes, the air cools, and the moisture swept off the water begins to form a cloud. As the tiny water droplets in the cloud come together, they become heavier and then fall to the ground. As the air skims down the other side of the mountain, it heats up and the cloud vanishes. The side of mountains facing away from oceans are often dry. In addition, a so-called rain shadow may stretch more than 100 miles downwind from a mountain range. Rain shadow areas are known for their dry lands and dry air. Oceans and large lakes, the fourth of the 5 factors that affect climate, often moderate what might otherwise be more extreme weather conditions. An example occurs in San Francisco, California, on the shores of the Pacific Ocean. San Francisco and St. Louis, Missouri, a city some 2,000 miles or 3,300 kilometers to the east, lie at about the same latitude, and so get about the same amount of solar energy each year. Yet San Francisco's climate is much less extreme than that of St. Louis. Summers are mild and winters are cool there, while in St. Louis, summers can be blistering hot and winters very cold. The difference is the moderating winds that blow off the surface of the Pacific Ocean. They act as a kind of giant air conditioning system. Or take the case of the British Isles, which for the most part have mild summers and cool and rainy winters. The northern tip of the Isles is located on a latitude that runs north of Moscow, Russia, a city that has cold, snowy winters and very short, cool summers. The contrast is caused by the warm ocean waters that flow by the Isles, waters that originate off Africa's west coast near the equator. Now, on to the Earth's winds, the last of the 5 factors we'll discuss that affect climate. There are 6 belts of winds that encircle the Earth. They push along warm and cold air masses, moisture, storms, and pollution. What are called trade winds meet near the equator, causing air to rise. As it does, rain clouds form. This band of cloudy, rainy weather near the equator is known as the doldrums.
All right, so thank you. That's it for today, and we will do some. I'll see you in class tomorrow.